So we've talked about how nonmetals and metals tend to form ionic compounds by transferring electrons from the metal to the nonmetal so that they both have a full outer shell. One of the problems that you might see is trying to work out the ionic formula of a compound whose name they give you. So let's get some practice doing this. I will start with some relatively simpler ones, and then we'll move on to more difficult ones. So the first one I want to look at is beryllium oxide. So given the name of a compound, how do you actually go about figuring out what the formula is? Well, we need to find out the ratios of the respective elements within the ionic compounds. Let's just see what I mean by going through this example. So I'm going to start by looking for beryllium and oxygen in the periodic table. So whenever you see the second guy here, this first guy is the metal, and this second guy is the non-metal. I'm just going to use M for metal, and M is non-metal. And notice the DE spelling here. Whenever you see the DE spelling, it just means that there's only one element in this thing, namely oxygen. So this is a combination of beryllium and oxygen somehow. So they combine to form beryllium oxide. So I'll look up the periodic table, and I find beryllium in group 2. Beryllium is element number 4, but what I'm concerned with is the number of electrons in its valence shell. Since it's in group 2, it's got 2 electrons in the valence shell, and indeed so beryllium has is element number 4, and oxygen is element number 8. And indeed, if I were to write out the electronic configuration for beryllium, I find that it is 2, 2. 2 and 2 makes 4, so 2 in the first shell. Next 2 has to go up to the second shell because the first floor can only hold 2 electrons, and indeed I find that it's got 2 electrons in the outer shell as predicted by its position in group number 2. And if I were to write out the electronic configuration of oxygen, I find that I get 2 in the lower floor, and I have 6 left over when these 6 have to go into the second shell, because the second shell can hold a maximum of 6. So I find that oxygen has 6 electrons in the outer shell as predicted by its position in group 6 of the periodic table. So I will concern myself not only with the outermost shell of electrons. So I'll write beryllium here, and I will denote its 2 electrons in the outer shell with 2 crosses, and oxygen here, oxygen symbol O, I will denote its electrons with dots this time, and it's got 6 dots. So beryllium will want to give up its 2 electrons so that its outermost shell is full, and oxygen is going to want to add 2 electrons so that it's got an overall 8 electrons in its outer shell. So they become good friends, and beryllium can give its electrons to oxygen. Now that beryllium has lost 2 electrons, remember it still has 4 protons, so beryllium still has 4 protons, but since it lost 2 electrons, it's now got 2 electrons. So since the protons are plus, and the electrons are minus. Beryllium now has a net charge of 2 plus, whereas oxygen got an extra 2 electrons. It's element number 8, but now it's got 10 electrons because 8 and 2 makes 10, so it's got a net charge of 2 minus. So we see here that beryllium and each beryllium is perfectly happy giving all of its electrons to one oxygen, and each oxygen is perfectly happy taking all of the oxygens from one beryllium. So the ratio in which they would react would just be 1 to 1. So we represent that as a formula by saying that beryllium oxide has formula BeO. Now I could have written Be1, O1, but the 1 is implicit. We only start writing numbers if you have 2 or more. So I end up with just BeO. Now we can go ahead and draw this diagram for each and every time you want to figure out the ionic compounds, but there's a shortcut that you can take by looking at the number of valence electrons in the atom. So beryllium wants to lose 2, hence it tends to want to form a 2 plus ion, while oxygen wants to gain 2 electrons for a full shell because it has 6. So oxygen tends to want to form a 2 minus. So what I'll do here is I will cross these numbers. I'll take this number down here. This is just, you know, a quick shortcut method that I like to use to figure out the formulas, and it works most of the time. So this 2 comes down to beryllium, and that 2 goes down to the bottom of the oxygen. Now I have 2 beryllium combining with 2 oxygen, but since the ratio is 2:2, I can simplify that ratio. So I'll simplify. The lowest ratio between 2 and 2 is 1 and 1, so I end up with 1 and 1, which I can write as just beryllium oxide. So I actually end up with the same formula here as I did if I were to figure out how the electrons kind of transfer. So either way, whichever method you feel comfortable with is probably the method that you should use, but this is a shortcut method that I like to use. For the next example, let's look at rubidium fluoride. So I have rubidium fluoride, and let's take a look at the periodic table. Rubidium is right here. It's a big molecule. I beg your pardon, it's a big atom. It's got 37 electrons altogether. But since it's in group 1, I know for sure that rubidium has 1 electron in its outer shell. So rubidium kind of looks like that, with 1 electron in its outer shell. And since it's got 1 electron in its outer shell, it's going to tend to want to lose that electron. So rubidium tends to want to form a Rb plus ion. It tends to want to lose that electron, and after losing that electron, it's got a plus charge. Whereas fluorine is in group 7. It's in group 7 there. Element number 9. So fluorine has 7 electrons because it's in group 7. So it's got 7 electrons in its outer shell. To form a full shell, it needs 8 electrons, so it needs 1 more electron. So fluorine tends to want to form an F minus. Just to be explicit, I'll write that 1 there this time. 1 plus and 1 minus. So using the first method, you can see that rubidium wants to transfer one electron over to fluorine. So after rubidium has transferred its electron to fluorine, it forms a 1 plus charge, and fluorine has an extra electron, so it's got a 1 minus charge. So you can see from here that each rubidium is perfectly happy with just one fluorine, because one fluorine can take its 1 electron, and fluorine only needs 1 electron, so it only needs 1 rubidium to be hanging around to make it happy. So the ratio of this rubidium to fluorine in a compound of rubidium fluoride would just be 1 rubidium to 1 fluorine. Hence, rubidium fluoride has formula RBF. And once again, we see that the DE here indicates that on this right side of the formula, we only have one species. We only have fluorine. It's not a combination of fluorine and something else. So this is the simplest we can get when you see the DE. Now, of course, I could have just done it a different way using a shortcut. Rubidium is in group 1, so it tends to want to lose 1 electron. So I put a 1 there. Fluorine is in group 7, so it tends to want to gain an electron. It's in group 7, it wants to gain an electron. Put a 1 there. Now I can switch these ones to the bottom, so I end up with RB1, F1, and I get the same thing. Next example, let's look at sodium sulfide. So just to make sure, this is DE, so I'm just going to talk about sulfur. So this is actually a combination of sodium and sulfur. Let's look in the periodic table and see if we can find sodium. Sodium's right here, element number 11, and it's in group 1. So sodium's in group 1, therefore sodium, let's check the symbol. Sodium is Na. Sodium group 1 forms as 1 electron in the outer shell. Sulfur is in group 6 here. Group 6, so it has 6 electrons in its outer shell. Sulfur, it's got 1, 2, 3, 4, 5, 6. So now we run into a situation where one sodium isn't going to keep this sulfur happy, because this sodium wants to give up its electrons to fill that spot. Well, sulfur needs 2 more electrons. It's got 6 electrons. It needs 1 more electron to fill that spot. So where is it going to get that electron from? Well, we need another sodium. So sodium's got to bring along its friend, another sodium, to give sulfur the electron. So in the process, sulfur has gained 2 electrons. So sulfur is now perfectly happy, forming a 2 minus ion, whereas each sodium has formed a positive ion, having lost 1 electron. So we see from this picture that the ratio of reacting elements in sodium sulfide is 2 sodium for every sulfur. So we need 2 sodium to supply the 2 electrons that sulfur needs. Hence we end up with a formula of Na2, because I need 2 sodium and 1 sulfur. But of course I can write this as just Na2S without the 1 on the S, because all the number 1s are implicit, so I don't have to write the number 1s. Now let's take a look at the shortcut way that I would have done this. Sodium is in group 1, hence it's going to want to form a 1 plus ion because it wants to lose that 1 electron. It's easier for it to lose that 1 electron than to gain 7 to get a full shell. And sulfur is in group 6, so 6 plus 2 is 8, and sulfur is going to want to form a 2 minus ion because it wants to gain 2 extra electrons to form a full shell. It's easier for it to just get 2 than to lose 6 of its electrons to get a full shell. So what I do now is I cross the 1 down here, 2 down there, and so I see sodium gets the 2, sulfur gets the 1, and this can be written sodium 2, sulfur. I dropped the 1 because the 1 is implicit, so I end up with the same formula as I did drawing the electron transfer picture there. Next, let's look at a slightly more complicated example. Let's look at calcium nitrate. Calcium nitrate. Okay, can't really see that. Let's write it again. Calcium nitrate. Now, in this case, you're going to have to recognize that nitrate is NO3 minus ion. So if you've not seen this, don't worry about it. You know, these tend to be fall into the category where of the ones you tend to have to memorize. So you know, as you see it more and more, it kind of sinks in and becomes second nature. So nitrate tends to form an ion with 1 minus, whereas calcium, let's look at calcium. Calcium is in group 2 of the periodic table, hence it's going to want to lose its 2 outer shell electrons, thus forming a 2 plus ion. So let's see if we can do this using the shortcut way. So calcium wants to form 2, nitrate wants to gain 1 electron, so I cross these numbers. So calcium gets that 1, and nitrate gets that 2. Now we have to be careful because the nitrate kind of goes together, and I want to make sure that the 2 refers to the whole nitrate and not just, you know, if I were to put a 2 down here, you know, we might get confused and think that it refers only to the oxygen. So I want to make sure that it refers to the whole thing, so I'm going to put a parentheses around nitrate and put a 2 out here. So now the 2 is going to refer to the whole nitrate conglomerate here, or how you would call it. So the 1 I can drop. So calcium nitrate looks like that. So that's the formula for calcium nitrate. So let's take a look at the next example. Let's choose aluminum oxide this time. So if I look at a periodic table, I find that aluminum is indeed a metal. It's just right below the staircase. Remember, everything below the staircase is metal, all the stuff here. Anything above the staircase is non-metal. Aluminum is in group 3, so aluminum tends to want to lose 3 of its electrons to whatever non-metal it is reacting with to form a 3 plus, because if it's lost 3 electrons, it's got 3 excess protons, so it gives it a 3 plus. And oxygen we've seen before, oxygen is in group number 6, so it needs 2 more to make the full shell 8, so 6 plus 2 is 8, so oxygen tends to want to receive 2 electrons to form a 2 minus ion. Now I can take the shortcut method here bring the 3 down there, bring the 2 down there, and I find that my formula for aluminum oxide becomes Al2O3, and since the ratio is 2 to 3, I can't simplify this anymore, so I'll just leave that as it is. That would be the formula for aluminum oxide. And as a last example, let's look at aluminum hydroxide. Aluminum hydroxide. Aluminum is, as before, tends to form a 3+ ion because it's in group 3. It wants to lose 3 electrons. Now, hydroxide is not something we've seen before, and again, this one kind of falls into the category of one of those ions that you need to memorize. So don't worry if you aren't familiar with it for now. Hydroxide refers to this ion, OH minus, and the minus collectively means the whole conglomerate OH here carries a minus charge, so I'll just make the 1 explicit here to aid our calculation. So to figure out the ionic formula, I'll take this 3 and I'll bring it down there, this 1 down here. So aluminum gets that 1. Hydroxide as a whole, don't forget to put the parentheses in, hydroxide as a whole gets that 3. So I can drop the 1. So the ratio, beg your pardon, ratio of aluminum to hydroxide is 1 to 3, so I end up with this being the formula for aluminum hydroxide. So I hope this video has helped you, will help you figure out the formulas of ionic compounds, translating them from words into the symbol form that we see here.